Welcome everyone to this week's Ask an Astronomer live stream. My name is Stefan Hammersheim. Today with me I have Sam, and we are from the Institute of Astronomy at the University of Cambridge. And we're here to answer all your questions about science, the universe and everything. So Sam, do you want to introduce yourself and say a bit about what your research is about and what topics you're interested?
Yeah, so hi everyone. As Stefan said, I'm Sam. I'm also a PhD student in Cambridge. I'm kind of personally interested in, probably the easiest way to think about it is the way black holes eat. So black holes are these kind of really cool objects in the universe, but they're also really hungry and they like to eat a lot of matter and grow bigger. And the way they eat is through they form disks of material around themselves, and these disks are the most luminous objects that we know of in the universe. But there's a lot about them that we don't really understand, and so kind of that's what I focus on in my work.
Yeah, it's going to be an exciting stream. For our new viewers to explain what we're doing here, so you can just go to the chat on YouTube or on Periscope or whatever other platform the stream is going on, and just ask us questions in the chat. We can answer them. And if you don't want to make an account on those, you can go to Slido. There's a link in the YouTube description. And there you can also just anonymously submit questions. Those are the ones here on the right. And yeah, so let's start. And while we're waiting for you to finish typing your questions, maybe you want to tell us about why are there kind of disks around black holes? So why isn't it just like a huge ball of matter being eaten, but why is it a disk?
Okay, so this is something which kind of technically we call angular momentum, but the easiest way to think about it is kind of spin. So material, you might think would just, if you have a black hole which is really massive with a really strong gravitational field and lots of matter around it, you might think that the matter would just fall straight down onto the black hole. But what happens is if that matter is moving slightly kind of in a direction that's not straight towards the black hole, then it would orbit the black hole in the same way that the moon orbits the Earth and the Earth orbits the sun. It would just keep going round and round forever. But what happens is, because there's lots of this kind of hot gas material, it can interact with each other through kind of viscosity, which is sort of the way that material pulls on other parts of the same material as it tries to move past it. Then what happens is that this material kind of settles down into a disk, which extends from very, very close to the edge of the black hole out to sort of very large distances. And what happens there is these viscous effects, so the disk pulling on each other as some bits are moving faster than the others, that dissipates energy. The disk gets very hot and it radiates this energy away, which is what we see. But because that material starts losing energy and it loses this angular momentum, then there's a net motion of this material through the disk inwards towards the black hole. And so this is kind of how the black hole eats. So it actually takes a lot longer than you might expect for the black hole to eat.
Okay, we already got our first question from YouTube. Which dies first, all the stars of the galaxy or the black hole in its center? So let's take the Milky Way, for example.
That is definitely all the stars in the galaxy by a very long way. So in terms of kind of the history of the universe, now Stefan is the cosmologist. He's the one to talk about the history of the universe. But my kind of very rough explanation of this is we're living in a very special age in the universe, which is sometimes referred to as the age of stars. So in the very early universe, which I don't know much about, there weren't any stars, galaxies hadn't really formed, definitely no planets. And then the stars started to form and we kind of formed galaxies, and we moved into the age we're in now, where we have stars grouped together into galaxies. And that age is going to continue on for a while longer. There's still a lot of gas which can form stars, so we're still generating new stars. But eventually we will run out of gas to form stars. And slowly kind of all the stars will die and galaxies will sort of fade away because there won't be new stars to replace those ones that have died. Now, the black holes in the center of galaxies, we used to think of kind of black holes as eternal prisons. So once something had crossed into a black hole, and it was never going to get out. So if any of you don't know, so a black hole is an object that's gravity is so strong that nothing can escape from it, not even light. And so it would seem that given that light is the fastest thing in the universe, that if light can't escape, nothing can get out of it. But sort of probably 20, 30 years ago now, Stephen Hawking came up with this idea for Hawking radiation, which is a really complicated effect. It's a quantum mechanical effect. And it basically means that over time, black holes will evaporate. And the bigger the black hole, the longer it will take to evaporate. But these black holes in the center of galaxies are so unbelievably big. They're sort of hundreds of millions of times bigger than the sun. And the sun is sort of 1 million times bigger than the Earth. So these are really colossal kind of numbers. It will take, for those black holes to kind of die, will take kind of many orders of magnitude longer than the current age of the universe. It's kind of times that you can't even hold in your head. So they will eventually die, but you know, so far into the future that certainly there won't be any people around to witness it.
Yeah, and we got also another question from YouTube about the movement of galaxies. So actually, yeah, that's a bit related to a question we had previously. So of course, we can see in the sky like galaxies are moving around and eventually colliding. So I mean, we have many images of colliding galaxies. And in the future, in the far, far future, so don't be worried, our galaxy will actually collide with Andromeda galaxy. So if you look in the sky and measure the velocity, the Andromeda galaxy is moving towards us, or we are moving towards it on a collision course. And I think in a few billion years we will collide. I'm not sure about the exact number. Yeah, then kind of we will kind of stay together. And what we call the local group are kind of our local neighbors of galaxies. So it's mainly the Andromeda galaxy and the Milky Way, and a lot of dwarf galaxies that are orbiting around it. And kind of this together is the local group. And they kind of two effects. So there's gravity that's pulling objects together. So of course all the local group objects will be pulled together, but also other galaxies that are further away from us will also kind of get pulled towards us by gravity. But there's another effect of the expansion of space. So space is expanding all the time. That's like a physical kind of basic, well, it's an effect that comes out of general relativity. And space is expanding with 17 kilometers per second for an object that's 1 megaparsec away from us. So for the Andromeda galaxy, this is like around 50-ish kilometers per second that it would be expanding away from just from the expansion of the universe, but it's moving towards us fast enough so it can overcome this expansion. And I'm not exactly sure, but I think all of the other galaxies, or all the major galaxies, they are so far away from us that the expansion of the universe is faster than their kind of velocity towards us, so they will not reach us ever. So essentially, they will come kind of, they're attracted to us, but the universe is expanding faster than they could come towards us. So, like no other big galaxies will join our local group. Oh, we got another question. That's one for you, Sam. What would a black hole dying look like?
Yeah, looking at the chat, we're getting a few black hole questions. So it's clearly a good week for me to be on. So a black hole dying is probably going to be uneventful, basically. So what happens in kind of dying black holes or evaporating black holes is you get really small kind of quantum particles, kind of just atomic particles, sort of electrons or things kind of that big, randomly released from the black hole. So we're never going to be able to see them, unfortunately, and they happen kind of so rarely and sporadically that they're probably very difficult to measure as well. So if you were able to kind of live for long enough to see a black hole dying, which is impossible, you just sort of see the black hole get gradually smaller over time. It's kind of a bit uneventful and yeah, a bit boring, really.
I mean, if we would be able to make our own black holes someday, then we could make really small ones that would die really quickly. But with the ones that stars give us, we won't be able to see them die in any like meaningful way.
Yeah, I should say, yeah, I'm interested in the big black holes.
Yeah, I mean, if we could produce small black holes, I think many people would be interested, but at the moment we don't have any way to make them.
No.
Okay, so we've got a Schwarzschild radius question. Do you want to take it or should I take it?
I'm happy to keep going.
Okay, there you go. Why is the
So
Schwarzschild
the
radius so
question,
special?
so the fundamental reason why the Schwarzschild radius is so special is because it defines what we call the event horizon. And I should be specific here. So I'm talking about a black hole that isn't spinning. So it's not going kind of round and round like the Earth does, rotating. And it's not charged. So there's no electrical charge at all. And under these kind of properties, this was actually the first solution to Einstein's general relativity that we ever found. It's quite a funny story that when Einstein developed general relativity, he didn't think it was possible to find a solution. And Schwarzschild managed to, not only did he find a solution within kind of 8-9 months, but he did it while being posted on the Eastern Front of World War One. He was in the Russian army, I believe, and he managed to find this solution on the Eastern Front. So I think shows you can do physics anywhere. But the reason the Schwarzschild radius is so special is because it defines what we call the event horizon. And so if you're closer to the center of the black hole than this event horizon, it means that light can't get out, basically. So it defines in the picture that Stefan's got up here. He just changed it.
I'll go back.
The standard picture you see of a black hole, you have this kind of black circle as we see it, and kind of light outside it. But within that black circle, that's within the event horizon. And so from within that region, light cannot get out. And so this is kind of what the Schwarzschild radius is. There's a couple of other mathematical peculiarities to do with it if you actually go through the maths, but it's not a kind of a physical peculiarity per se. If you were heading into the black hole from a long way away, then as far as we know, you wouldn't know any different as you cross the event horizon. All it would mean is that when you were inside it, if say I sent Stefan into a black hole on a holiday, and so he'd be on the phone to me or be sending light signals out to me, then he'd be fine crossing the event horizon from his own point of view. He might be getting a bit stretched due to kind of tidal forces that stretch things, but he'd otherwise be fine.
It's called spaghettification, I have heard.
Indeed, it is, and you can kind of see why. You get turned into just a piece of spaghetti in shape. But in terms of the signals heading back to me, as soon as he crossed this event horizon, I would no longer be able to hear from him. I could still send him messages in, but he wouldn't be able to talk to me anymore. So obviously I would never do that to Stefan. But
that's just nice.
If I did, he wouldn't be able to talk to me anymore.
Yeah, we got just the follow-up question. How does it change if it has spin or charge?
So this is difficult. This is where the math becomes more difficult. So in terms of astrophysics, we don't care about charge. So if you ever had a charged black hole in space, then it would very quickly, because electromagnetic forces or kind of electric forces are much stronger than gravity, it would very quickly kind of pull in charged material from around it and become charge neutral. So there are solutions if black holes have charge, but we don't care about them in terms of astronomy. But for the spin, there is a solution. It's called the Kerr solution as opposed to the Schwarzschild solution. It's more difficult mathematically. And what it basically means is that this event horizon becomes smaller by up to a factor of 2. So if this black hole is spinning very, very fast, then this event horizon can become smaller by a factor of 2. It changes the kind of dynamics of what's going on around it. So there's a concept called frame dragging, which is basically means that even if you're outside the black hole, because the black hole is spinning, it's actually pulling what's called space-time with it. So it kind of pulls the space you're moving through with it as it goes round, as far as I understand it. And so it kind of mucks up all of the dynamics that happens outside it. But the main thing it does is it shrinks that event horizon down by a factor of 2.
Yeah, I think like black holes are really, really exciting objects. It's always so like there are really lots of unexpected and crazy things happening. While we're talking about like really old things, we attracted a lot of questions about what will eventually happen with on really late timescales. So we got a question about will there be any subatomic particles present in the universe? after the last big black hole evaporates, or let's say how the universe kind of looks like in general?
I'm gonna say that I'm not certain on this. I think there's a lot of unknown particle physics on these kind of long timescales that's still unsure as to whether these subatomic particles will survive or not. These are timescales which are just kind of unbelievably long. I can't remember exactly, but just ridiculous. I'm not sure if you have any clearer idea.
It's just many, 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 many times the age of the universe. So like with loads of zeros, I have no idea. Yeah, but essentially, I guess you will just have like, so you'll have the Hawking radiation coming out of the black holes, and this will fall into whatever is like the lowest entropy, or I guess like these energetic states, but I'm not sure what exactly will happen. In particular, there are some questions we don't know the answer yet. We got also a question: do you think proton decay will eventually occur? So that's actually a really interesting story. Protons are elementary particles, so all the matter that you and I are made of is essentially protons, neutrons, and electrons. Yeah, I think that's it. And well, initially people were like finding out how the standard model looks like, what are all the properties, and they found out, okay, there would be a nice theory that includes all the forces, I think also gravity, but it also would imply that the proton decays. It's called the fifth force theory. And it was really attractive, like it would be a really cool theory, and it would be really simple. So people started building detectors for it. Actually, I can show one of those detectors here. And yeah, they built huge tanks of water or other atoms, like I think xenon or something, and put like lined the walls of those detectors. So what you can see here on the screen, that's Kamiokande, essentially a huge tank of, I think, water with walls lined up with photo detectors. They would decay photons that get emitted if a proton decays. And the timescales expected were like years, so protons would decay on year or many, many years timescale. But since you have so many protons, you would expect that you would eventually find a decay in this big tank of water. And we didn't find any proton decaying. So if they decay, they decay really, really slowly. But my belief probably would be they probably don't decay because we didn't see the decay yet, and just saying the decay is smaller and smaller is kind of fine-tuning. I mean, it's just saying the rate is lower than the experiment. So we don't know, but I don't think just the simple way would be they don't decay. Oh, we got well, we should also take a few questions that are not from YouTube, but from Slido and Periscope. So we got, of course, our obligatory aliens questions. Do you think aliens exist? And if you do, would you look for them? I think aliens do definitely exist somewhere. I don't think we'll find them in the near future, or in the near, like, next, I don't know, few billion years, maybe, probably not, just because the universe is just so huge, and distances between galaxies are so huge. But since we think the universe is, like, well, we don't have any reason to believe that the universe is kind of finite in space. It could be just infinitely large. And even the observable universe is just huge. So I think there's a good chance that there's some life out there, but I don't think we'll meet it anytime soon. Yeah, we got one from LIGO. Has LIGO been able to measure... well, no, we got a question from Periscope, but it was about LIGO. Has LIGO been able to measure any black hole spin? And has LIGO been measured to be... yeah, or frame dragging? Oh. So...
I think the answer is yes to this.
Oh.
In terms of the spin. So I think what LIGO do is they have a lot of kind of theoretical models for what merging black holes should look like. And then they try and see which one of those models gives the best fit to the data. And that includes all sorts of ways the black holes are orbiting each other, and they can be orbiting each other and each spinning in all kind of potentially different directions. And so I believe that when LIGO publish their results, they include some kind of estimate on how much the black holes are spinning, and that they do find that they are spinning. In terms of measuring frame dragging, it's sort of an effect that is a result of the theory. So it's kind of one of those things that would go into LIGO's models when they try and determine things. So I think, as far as I'm concerned.
would this frame dragging appear like when you make a photograph of the black hole, like that the Event Horizon Telescope did? Is frame dragging responsible for that the one side is brighter than the other?
That's an excellent question. So I think the primary effect for why one side is brighter than the other is if you imagine this disk that I talked about kind of right at the beginning of the stream. If you imagine that kind of one side is heading towards you, if you're looking edge on, imagine you're kind of looking at a spinning frisbee edge on. One side might be moving towards you and one side is moving away from you. And these are moving incredibly kind of fast at a relativistic speed, so a not negligible fraction of the speed of light. And so some of these are what you call Doppler boosted, which means that as they're coming towards you, or as the material that's emitting this light is coming towards you, it's actually boosted to higher energies, the photons that are given off, than the material that's moving away from you. I think that's the primary effect for why you kind of would have one side brighter than the other. In terms of the frame dragging, I think in the theory, kind of there are theoretical models which trace what the light would be like through these kind of around a black hole, and that would include some effect due to this frame dragging, but I'm not certain kind of what the relative kind of contributions of those effects would be.
Okay, yeah. I just noticed that I talked about LIGO again without explaining everything, so I should mention this again. So LIGO is a gravitational wave detector, which is a really awesome piece of kind of technology. And what we know is, or what Einstein's field equation tells us, and what turned out to be true, is if you have two really massive objects like black holes or neutron stars, or in principle anything like stars, but they're just weaker, if they orbit each other, they emit gravitational waves. And these waves kind of change the kind of size of space-time. So if a gravitational wave passes through you, you would kind of shrink for a bit or grow for a bit for like a really tiny amount while the wave passes through you. And this is really nothing you can notice. But if you build a really precise detector like LIGO, so this is a kind of two laser arms, 4 kilometers long, at a 90-degree angle. And when a gravitational wave passes through the whole Earth, then it will stretch space in one direction, but not in the other. And this essentially would make one of those arms contract and the other not. And there are lasers inside who are really precise and measure this length exactly. And LIGO can see the change of length between the two axes and then measure that there was a gravitational wave. And then you can find out where this has come from, and it usually fits to merging black holes. While we're talking about black hole, does the temperature ever change in a black hole?
Yes, in a short answer. This is more of kind of the work that Stephen Hawking did. Was he kind of created an analogy between like the laws of black holes and the laws of thermodynamics, and this gives black holes a temperature, which is then the temperature of this Hawking radiation. So yes, they do have a temperature. I think it's very small, although I can't say I actually know the numbers off the top of my head, but it's not a kind of astronomically relevant temperature, should we say. It's in the kind of study of black holes, there's certain people who are really interested in kind of the maths and the really intricate details of how black holes work. And then this temperature is really useful. I'm more interested in kind of the effect black holes have on everything around them. And so this kind of Hawking radiation, this temperature isn't really relevant. It's such a tiny effect compared to everything else that's going on. Yeah, but yes, they do change their temperature.
And do you know what happens when a black hole has charge, and how can we detect this from Earth? Or can we detect it at all?
So I don't know off the top of my head is the answer to that question. I suspect that what would happen is if you had a charged black hole, then it would, if you had say a black hole that was positively charged, and you had some kind of plasma of protons and electrons in it, then it would pull the electrons towards it and push the protons further away.
Oh, yeah.
I'm not sure if this would be detectable, but as I said, we expect that. So because the electric force is so much stronger than the gravitational force. Even if you had like a black hole which had like some really small charge, then it would very, very quickly sort itself out and pull this in. So you wouldn't expect it ever to be observable. And so I don't think anyone's ever really looking for it. I mean, if we did observe a charged black hole, then we'd have to really think hard about that. And that would probably come up with a paradigm shift for what we know about the way black holes eat.
Yeah.
But I don't think anyone's expecting it. And I don't think there's any kind of evidence for it yet.
Yeah, I think no one has found charged as any evidence for this yet, yeah. We got more questions, black holes. So we got one about primordial black holes, so what are the implications of observing those? And maybe connected to that, how we detect black holes at all, so what's the kind of major source of data? So I mean,
Okay.
One of the sources we already discussed is like this LIGO experiment where we can detect gravitational waves from black holes that merge. But especially when you think about primordial black holes, which could be all kinds of sizes. So there could be like really small, like kind of masses of asteroids. And actually, I recently was a talk where someone told me, when you have an asteroid mass black hole, it's really, really tiny, and its gravitational effect is almost nothing. Like it could pass right through a human and you wouldn't notice. Like it's absolutely really ridiculously small, and like it's just the gravitational force is not really strong, and other than that is really, really small. So well, I should maybe confirm that before I let someone shoot a black hole at me. But I think it's really like really hard to find. And there are people, they're looking at so to detect primordial black holes in kind of not necessarily this size, but a bit bigger, but not like solar size. You could look at a patch of space and watch for the lensing that comes from black holes. So when light passes through black holes, or if light passes next to black holes or next to any massive objects, it gets lensed and curved, and this kind of changes the path of light you can detect. Mostly that some parts of the sky get like brighter, well magnified, and you could observe this. So just point a camera at a boring patch of sky all day and wait for something to happen. Do you want to say more about these questions?
Yeah, so on the primordial black holes point of view, I think it's interesting cosmologically. There's various people who would expect us to have primordial black holes and other people who maybe disagree. So it's interesting from that point of view. From kind of our point of view on looking at black holes in the as I said, the age of stars, in the centers of galaxies, and kind of black holes formed by dead stars and etc. Like in terms of observations, a black hole is a black hole. It's kind of where it comes from is very kind of known, impossible to discern from looking at it now. And so they could be useful. They could have an impact if they are there on what we would expect to see later on. But I think it's quite difficult to come up with looking at this black hole and like, did this come from a star? Was it a primordial black hole? You know, there's no real way of doing that. But kind of, so the question about the source of data used to study black holes, like Stefan mentioned LIGO, and this is very much a new effect. But the main way we look at black holes is not by looking at them. I mean, they're black, but by looking at the material that's going around them and looking at the light that comes off that. So these are kind of the most powerful objects and the most luminous objects that we know of in the universe. And to give you kind of an idea of how much energy we can get out of them. So in kind of nuclear fusion, so that happens in the sun, or that unfortunately, you know, was developed into nuclear weapons in the 20th century, you can get out an amount of energy that's equal to 0.7% of the amount of mass, and corrected by a factor of the speed of light squared. So the total potential energy, if you could turn all this mass into energy, the sun managed to get out 0.7%. A non-spinning black hole can extract 7 or 8%, somewhere in that region, of the total amount of energy from matter. And a black hole that's spinning very fast can extract kind of 30 to 40% of the energy from the matter that's falling in towards it. So this is kind of 10, 20, 30 times greater than the sun extracts. And so these are really, really powerful objects. And as a result, in some cases, they can get really, really hot. So kind of somewhat, you might think paradoxically, smaller black holes, the material around them gets hotter. And the reason for this is because everything is kind of joined in much closer. It's smaller distances. And so you kind of have more energy crammed into the same amount of space. And so things come hotter. And so we observe those in the X-ray, really high energy radiation, the same stuff that you get if you've broken your arm. And then kind of larger and larger objects, that tends to move maybe into optical. So we use visible light. And we're really looking at, in this picture, we're looking at the material that comes off this disk here. The subtlety to this is that you can see that on this picture, the bottom of, there's a kind of jet going up to the kind towards the top left of the photo, and the bottom of it is glowing quite brightly. And this is a kind of theoretical prediction that there's what's called a hot corona there, and that this also emits in the X-rays. And we see this because we observe X-rays where we don't expect them to do, and we can do some really quite clever kind of mathematical techniques to look at kind of the time delay from radiation that's emitted straight from this object to our eyes or to our telescopes, and radiation that bounces off the disk on its way to our telescopes. But we don't have a good explanation for that really as of yet. We just kind of see it there. So that complicates things. But by and large, the data we get is from X-ray telescopes or optical telescopes, the main two. Yeah, so we're not really observing black holes at all. We just know it must be a black hole because it's so big and so small that it couldn't be anything other than a black hole.
Yeah. So is there a way that we can kind of measure the how much an object bends the space-time more or less directly, and or calculate this from the black hole? And well, connected to this, why is it that smaller black holes bend this more? So that was a question we got from the website.
So we can certainly observe the way that this kind of bending happens. So this is what's called gravitational lensing. I think you mentioned it earlier, and certainly we can see. This is more, we observe it when you have a big galaxy kind of in the way between us and a really distant luminous object. And so I don't know if you can have kind of, I'm trying to do it with my hands on screen. So if you have kind of the really luminous object over here and us over here, then light can kind of go up and down and below kind of around it, and it kind of gets pulled down. The gravity has this effect on light and pulls it round on its way to us. So we could see this theoretically in the same way around individual black holes and individual objects. We haven't yet observed this, and I don't think it's kind of these black holes, we see them in the middle of galaxies, so it's the whole galaxy having this effect.
Yeah.
The question why small black holes bend more than big black holes, I'm going to believe you that this is true. I didn't know that this was true.
Yeah, so I think if you think about the Schwarzschild radius, which is kind of just scales with the mass of a black hole. So when you have a mass that is double the weight of a black hole, it has also double the size of the Schwarzschild radius. So all the effects that kind of make this curvature of space happen all kind of scale out, it gets stretched out even more. And if you think about the surface of a black hole, the surface scales with r to the power of 2. So if you have a black hole that's 10 times as heavy, the surface will be 100 times as large. So all the crazy effects will happen much closer, like the effects that happen at the Schwarzschild radius will be much weaker, and the kind of, if you look for a point where the bending of space-time is the same strength, this will be much inside the big black hole and on the kind of outside of the small black hole. So that's why for small black holes, more of the crazy stuff is, let's say, exposed, as opposed to large black holes, where most of it is inside the black hole event horizon. Actually, when you want to throw me in the black hole one day, Sam, please take a large black hole, because, well, for your own sanity, because then crossing the event horizon isn't really that, well, peculiar for myself, because the black hole, the event horizon is so far away from the center of the black hole that you don't even feel that much of the curvature at that point.
I'll bear that in mind for your next holiday, when we're allowed to travel again.
Yeah, right. From Slido, we got the question, is there a black hole cluster anywhere in the universe?
Not that I know of. Not that I think anyone knows of, but I don't see a reason why there couldn't be, fundamentally.
Yeah, I think like usually if you have black holes, there's not really a way. Like I mean, obviously, like I mean, if you think about black holes, so black holes are usually get born from stars, and stars get created in galaxies. So in a galaxy, you will have loads of more black holes than, let's say, in a void or in an otherwise empty region of space. So that's kind of a cluster of galaxies. Or when you think about galaxy clusters, of course, all those galaxies have black holes. So also this cluster is also a black hole cluster, but nothing that would like intuitively think of like many black holes in a small space. That usually doesn't happen. Also, when you think about black holes orbiting each other, it's really hard to get more than like two things orbit each other. Like when you have 3 or 4 items in a system of orbits, often one gets kicked out and flies away. So I think you don't have a really small cluster of black holes.
Yeah.
Yeah. Hello to England. We got greetings from the YouTube chat. So let's take another YouTube question. Are there other ways to create a black hole than dying stars?
This is the $1 million question. So this ties into kind of a problem that some people think exists and some people don't think exists as a problem in terms of how we form some of these really big black holes. So there are black holes which are kind of a few times bigger than the sun, which form from dying stars. And then there are black holes we observe actually in the very early universe, so formed maybe only a billion years after the start of the universe. For kind of reference, we're now kind of 13, 14 billion years after the start of the universe. So really kind of quite early on in the life of the universe, that have masses up to 100 million, maybe even 1 billion times the mass of the sun. And there's a problem here because you either have to form these black holes very massive, or you have to form them at a lower mass and then grow them really fast. They've got to eat a hell of a lot of material to get that big. And so there's a few different ideas where these black holes come from. One of them is that they're just the remnants of the very first stars that ever formed in the universe, these so-called population 3 stars. So that's one possible explanation, and it's potentially okay, but they would form at quite low masses, and they'd have to grow an awful lot to kind of create these black holes that we see. There's kind of 2 other options which are debated theoretically as to whether they're plausible or not. There's still a lot of uncertainty, and we have no observational evidence for them at all, because they would have happened very early in the universe where we can't see them. One of them is if you just have a really big cloud of gas that's not spinning. So I've mentioned it a lot that spin plays a havoc for kind of collapsing things down on themselves. But if you had very little spin and a very big gas cloud, some people think that you could just collapse that straight down to form a black hole that's maybe 10,000 or 100,000 times the mass of the sun. So it still needs to grow by another factor of maybe 1,000, but that's a lot better than having to grow by a factor of 10 million. And then there's one suggestion which kind of lies somewhere in the middle, which is that if you had a star cluster in the early universe, so just a lot of stars in a very small amount of space, then what happens due to dynamical interactions is that some of the stars fall kind of towards the middle of the cluster, and that these could collide and form something which is called a very massive star. Like, astronomers were very kind of inventive with the names we give things, so very massive star, and that this would explode very quickly and form a black hole that would maybe be 1,000 times the mass of the sun. So it's kind of somewhere between the 2 extremes. It's maybe more likely than this direct collapse model, but it would give a slightly more massive starting black hole than the remnants from stars. And I guess the other option, which we mentioned earlier, is potentially just primordial black holes created kind of at the very start of the universe. But yeah, so I think they're the options that we currently think about. There could be others that no one's thought about yet, but
yeah. Okay, so we got another few questions. First, yeah, hi Caro. Then we got a question from from on Slido about adding more math in our videos. For now, let's stick to we'll try to stick to more kind of accessible and like visual displays with our hands. When we are back at the institute, maybe I'll write 1 or 2 equations on the board, but I'll try to keep it to a minimum. Then we got a few cosmology questions since a few minutes, so I maybe should talk about those. So one from Periscope: is there any advancement in the last couple of years that you're excited about? Yeah, certainly there are some really nice, fields that are emerging now. I mean, gravitational waves are kind of old already, but there's still a really active field, and there's a load of stuff to be discovered, like with all the new detectors we can build. There's 21 centimeter cosmology, which is actually the field I'll be working in. So that's taking the neutral hydrogen in the universe. So maybe I should give a bit of background. Up until when the cosmic microwave background was emitted, so a few 100,000 years after the Big Bang, the universe was ionized. And after this time, so a few 100,000 years after the Big Bang, the universe kind of cooled down and became neutral, full of gas that didn't do anything in particular. And only a billion years later, this gas collapsed into stars. Like, it took a billion years for this gas to collapse to form the first stars. And that's kind of really long. Well, might have been a bit faster, but it's in general a really long time. And then we can make observations. So our best observations our furthest observations go back to a few billion years after the Big Bang, I think. And everything in between is mostly unexplored, really unexplored. And observing this neutral hydrogen that's all around there in the universe would give us a really new great picture. Yeah, so there are loads of fields in this cosmology that they're getting. I can't name them all, so sorry if I forgot some now. But yeah,
I think in general, as astronomers, we're always waiting for the next telescope as well. So I think so many people are fingers crossed for James Webb Space Telescope when it kind of eventually goes up, and then it's always just looking forward to the next generation of telescopes, because each one, it reveals kind of so each telescope that goes up answers some questions and poses more, because it kind of slightly sees things that we don't really understand, and so the next one to go up kind of tries to answer the ones that were posed by the previous one, and then kind of it poses some more. So it's kind of this never-ending cycle.
The same is, of course, true for cosmology. Like, we're waiting for LSST, at the Vera Rubin Observatory, for I think it's called something with the Nancy C. Roman telescope, previously called WFIRST. There's Euclid, the measurement that will be mapping almost all of the galaxies in the observable universe and allowing us to get a much better picture of kind of our cosmological neighborhood. And actually, that ties into one of the questions we got on YouTube. If we get more and more knowledge and see more and more of the universe, and we make our theories based on these observations, is there any way to test those theories afterwards? Because, if we observed all the galaxies, then figured out a theory, then there are no more galaxies we can add to observe it, to test it. So I think that's a really interesting question, and essentially, that's kind of why we have so much so-called Bayesian statistics in cosmology that kind of tries to figure out, okay, is this model actually really predictive, or is it just kind of a post hoc fit to our observations? I think that's working reasonably well. And also, you can always test your theories with new observations that you didn't think about before. So, say, lots of theories of gravity that were made for kind of fitting the observations of galaxies and their movements get tested now by gravitational wave experiments and often ruled out. Because, for example, they didn't predict that the speed of light and the speed of gravitational waves would be the same. Yeah, so that will be really interesting. And now we got a ton of questions on YouTube, and I didn't even get to read them all. Do you want to go ahead, Sam, and take one of those?
Yeah, so there's another $1 million question coming here, which is came in kind of 10 minutes ago. Does a black hole trigger the formation of new stars and planets in the region around its orbit by pulling in gas and dust closer and closer? I would love to know what role a black hole has on the environment around it. No one knows is the answer to your question. And it's kind of whether it could trigger star formation or whether it could suppress star formation. This is kind of positive feedback or negative feedback. No one really knows. There's so many different competing effects because it's not only the gravitational influence, it's the fact that because so much energy is liberated by these black holes as material falls in, they're actually pumping energy into the galaxy around them. And the effect this could have on the gas around is really not very well understood. There's lots of people trying to simulate it, lots of people trying to observe it, and everyone seems to disagree with everyone. And a new result comes out fairly regularly, which claims to kind of have changed everything around. So I wish I knew. If you find this out, can you tell me first? That would be great.
Okay, so we got a few kind of career questions. We talked about this a bit last episode, but to be honest, we can't really give that, can't really answer the questions with kind of confidence because we are just students here and we are not really involved in any of the kind of selection process, so our knowledge is kind of limited about that. But you can find, of course, like those informations usually on the kind of websites or on with the colleges or with the university. For wet finding, we got one question. This sounds interesting. If you had a machine to travel infinitely in one direction, would you eventually get absorbed by a black hole? Is this inevitable? I mean, it depends on how your machine works, I guess, right? So the first point is, does your machine go with the speed of light, or does it go faster? If it goes only with the speed of light, only in quotation marks, it will take really, really long until you hit something at all. If you get absorbed by the first object you hit, I mean, you'll probably hit some gas. You might hit a star at some point. And I think it will take much, much longer until you find a black hole. But eventually, like, if you assume the universe is like infinitely large, which is probably a reasonable assumption, like we can only observe to a certain limit. So the speed of light is only 300,000 kilometers per second, roughly. So
only, Stefan, only.
There's a cosmologist in me. Well, it would be nice if it would be faster, but it's not. So we can only observe roughly like a few billion light years. So I think it's around 90 gigaparsec, which is I think 200 something light years, or maybe 300 something light years, into the past, because that's kind of where the universe began, and then the radiation just reaches us. So actually, the cosmic microwave background is the furthest away we can see with like normal radiation, and even with something like gravitational wave, we can't see that much further. So there's kind of a limit of the observable universe, but that doesn't mean that the universe ends there. We just can't see anything further than that point. And yeah, if the universe goes on forever, you will eventually find black holes, you will eventually find life, you will eventually hit everything. But yeah, I think such a machine, especially if we think about normal technology, going with the speed of light or less, it will be a really long journey. Okay. So what else do we have?
We got a bit. What I think we missed earlier. Kind of quick question again: whether there's a theoretical limit to the minimum and maximum mass.
That's a cool question.
A black hole can have. On the maximum front, I think that's the easiest one to answer. The answer is no. As far as I'm aware, that's what general relativity kind of predicts. If you can get enough mass into the black hole, it will keep on growing. The minimum side is where we start to run into problems, because as soon as you start dealing with the very, very small, we start having to worry about quantum mechanics. So there's kind of I guess a few things which could set let's say start with kind of general relativity doesn't say anything about minimum mass as far as I'm aware. But then general relativity doesn't really consider particles, or kind of you can have as much or as little mass as you like. So if you actually tried to make a very small black hole, I guess the first problem we'd run into is very small black holes evaporate very quickly by this Hawking radiation. And so even if you could create one, it wouldn't last very long. You'd also probably have to kind of start running into a problem on kind of black holes who, like, mass is expected to be kind of quantized in the sense that you can't have as much of you as you like. It's not a sliding scale. It's more like having apples. So I can have 2 apples or 5 apples, right? So the same kind of thing would happen with mass, although on a much smaller scale. And so kind of quantum mechanics will kind of impose a minimum limit. But it's so far below kind of what we would expect, kind of what we can kind of physically realize. Actually, I saw a great, I read it in a book once, if you want to try and get a sense of how small things can go. So if you imagine like a full stop in a normal kind of book, like a novel-sized book, the full stop in the page there, the relationship between the size of that full stop and the size of the observable universe, in terms of how many times bigger the observable universe is than that full stop, is very similar to how many times bigger that full stop is compared to the smallest possible length that we think we could possibly have. And that, when I read that the first time, that like blew my mind. So the kind of, yes, there probably is a minimum mass for a black hole, but like it's so impossibly small that essentially the answer is no. But some people will care about what happens in those really small masses.
Yeah. Oh, so were there any gamma ray bursts present in the early universe? Do you know about? Do we know how gamma ray bursts get created?
So, no, kind of, maybe. I think depending on who you talk to. So up to a few years ago, I think the answer would be no. People had theories, but people weren't sure. So gamma ray bursts, for anyone who doesn't know, are just a random flash of gamma radiation that we observe in the sky. Now, gamma rays are the most energetic form of light. So we've got visible light, and then if you get more energetic, you go to ultraviolet, and then to X-rays, which is what I've talked about quite a bit. And then even further, we go to these gamma rays, incredibly high energy, incredibly dangerous for humans. They're kind of ionizing radiation. You don't want to be anywhere near them. Some people may like kind of play around with this kind of stuff in school labs with radioactive materials, with like Geiger counters and stuff. But yeah, so these very high energy radiation coming from somewhere on the sky for a short amount of time, basically, and people really unsure where they came from. Since LIGO, we've had one LIGO event which was not merging black holes but merging neutron stars. We're actually having something which is not black holes. So these merging neutron stars, and because neutron stars, because they're not black holes, light can escape from them as this kind of merging happened. And there was an associated gamma ray burst, I believe, which was associated with this event. It came at the same time and from the same patch of sky. And so there's an idea that some gamma ray bursts could come from merging neutron stars. I think there's enough difference between different types of gamma ray bursts that people don't think this is the source of all gamma ray bursts. And so I think a lot of them, it's still very unknown. And because it's very unknown where they come from, I'm not sure if anyone really knows whether they would have been around in the early universe.
Yeah, I think on general terms you could say, I mean, gamma ray bursts must come from really small objects, like they can't come from like huge galaxies or something, because they happen in such a small time that something has to happen like in a small object, because if the object was large and something would happen at one end, it would take quite a long time for the information to get to the other end to kind of, well, coordinate some whatever physics reaction, that this would necessarily be a kind of long signal, and gamma ray bursts are really short. So they have to be really small objects. And if we like okay, let's say, like if we don't take into account like special theories that involve primordial black holes or something, there aren't really any kind of small heavy objects or small very energetic objects in the early universe, because up until redshift of, let's say, 50 or 30, like that's a billion years or so after the Big Bang, you just have like a lot of gas that's kind of falling together slowly, but that's not really dense and small objects. And then you get the first stars and the first galaxies, but I think like it takes quite a while until you kind of form really heavy black holes and quasars and all the crazy things. So without kind of crazy objects, you can't have those crazy events like gamma ray bursts. So that would be my answer, but I'm not an expert in this. I have never like studied gamma ray bursts actually in science. So, actually, well, I read a paper recently that used gamma ray bursts to map out structure in the universe. So it's really interesting. So actually, the largest structures we know in the universe are found with gamma ray bursts because they are kind of so energetic and we can see them so far out. At least that's how they kind of found various large walls and structures. I'm neglecting lots of questions again. Oh, well, there are lots of questions. We got a question: can antimatter form black holes? That's cool.
Yes, and theoretically, antimatter can form everything that normal matter can form. So mathematically, if we do this mathematically, the only difference between normal matter and antimatter is that some places you might have a positive, you have a negative, and some places you might have a negative, you have a positive. So rather than protons being positive and electrons being negative, be the other way around, but that's fine. That doesn't really matter, you know, because positive orbiting a negative is just as easy as a negative orbiting a positive. So theoretically, yep, we could form antimatter stars, we could form antimatter planets, antimatter people. It is all theoretically possible. And so, yeah, definitely you could form antimatter black holes. Kind of what matter is like actually inside a black hole is, again, quite a difficult question. So I'm not sure kind of whether that's fundamentally different from a normal black hole. Like if an antimatter black hole met a matter black hole, I'm not entirely sure what would happen there. But theoretically, yes, you could form a black hole. Let's say you could form a black hole from an antimatter star. Let's say it that way around. The reason we don't is just by some, it seems, kind of random quirk. We just have more matter in the universe than we have antimatter.
I mean, we don't see any antimatter flying around except for the occasional cosmic ray. Like if we look in the universe, if there would be a galaxy full of antimatter, then we would expect that wherever the antimatter and the matter hits, we would see lots of light being emitted. But we don't see it, so there seems to be no antimatter, which is actually a big riddle in cosmology, or in the kind of models of the universe. And because we would think, okay, in the beginning, we know in the beginning we had lots of antimatter and matter, and eventually they annihilated, and lots of energy was emitted, but they didn't annihilate completely. So a bit of matter was left over, and apparently no antimatter. So maybe there's something in physics that actually prefers matter over antimatter, but for now we don't know, and it's kind of a riddle at the moment. And while we're talking of weird matters forming stars, can dark matter form black holes? And actually, I think we got a question on the website as well, if dark matter can form structures.
I don't see why not. All you need to form a black hole is a lot of matter and not very much space. And provided you get enough of it in a small enough volume, you will form a black hole. The gravity will be strong enough. You couldn't form a dark matter star, though. The thing with dark matter is it only, as far as we know, interacts with by gravity. So there's none of the kind of electric forces that you'd need to form a star. So getting a lot of dark matter in the same place is kind of very difficult because they only interact via gravity. And the thing is, yes, gravity could pull things together in a way, but there's no way of getting rid of that energy. So it's just going to fly through each other and out the other side. So to form these kind of stars and stuff, you need some way of dissipating the energy, which is kind of things colliding with each other. And dark matter doesn't collide. But certainly if dark matter kind of went into a black hole that already exists, yeah, it would stay trapped there forever.
Okay, so you could even form a black hole out of pure dark matter if you had a way of putting the dark matter in an object, because it won't do it for itself, because it will just it will just fly around.
I don't see why.
What happens when a normal matter person and an antimatter person shake their hands? Do they annihilate or something? That's gonna be a really violent handshake. So the first problem is, how do you get the antimatter person and the matter person to shake hands? Like, how do you get them on the same place? Like, if we meet on Earth, the antimatter person will annihilate with the atmosphere. If we meet on anti-Earth, the matter person will annihilate with the atmosphere. So let's say we meet in vacuum or space, and we have like space suits, but then do the space suits kind of lose atoms that fly towards the other space suit and annihilate? So it's kind of a messy part already to set up. And yeah, you don't want to be anywhere near when the antimatter and the matter person shake their hands, because it's going to be a huge explosion. So
like going back to kind of what I said, sort of quite early on in the stream about how much energy you can get out of material. So I said the sun can get 0.7% of the energy out of any material. Black holes maybe up to 30 or 40%. Kind of antimatter, normal matter meeting, you get all of the energy
100%.
out of the matter. So all of that matter just gets turned into light energy. And so that's going to be a really, really violent meeting.
Yeah, let's not discuss about consciousness of antimatter people. I have no idea.
Yeah. Consciousness is one of those things that I kind of read about when I want to find something I don't understand.
Yeah, so essentially it's like with every kind of explosion, it's not healthy. So let's not do that. So we have some speculation about negative matter. So I guess it's meant negative mass matter. I read about this once in a while, and half of the time it's usually like very speculative. Do you know anything about negative matter, and if there's like wormholes and stuff?
So I think kind of with wormholes and things, it's one of those things which mathematically people can find these weird and wonderful solutions to the Einstein field equations, which seem to govern our universe when it comes to gravity and space and time. And like you can manipulate the maths and come up with these weird and wonderful solutions, but there's no way of going from our universe to these solutions. Like that's mathematically impossible. So there are things like, I think this goes for wormholes and white holes and all these kind of things that you think about, or people do think about. It's kind of, they are theoretically possible to have. It is a solution mathematically, but unless they were created when space-time itself was created, unlike black holes, there's no way of forming one out of our current universe, which I think is quite thankful. I think they'd kind of muck everything up if we suddenly had wormholes.
It would be exciting. Okay, on that note, it's 8. Well, depending on what your time zone is, it's 1 hour after the start of our stream. So thank you everyone for viewing and for all the questions. Thank you, Sam, for being here and answering so many of the code questions and being a great person.
You're welcome. It's been good fun.
We will be here next week again, so join us next week, Monday again, same time, same places, to get rid of all our questions that you collect over the next week. If you want more astronomy things, tomorrow there will be a live stream of Matt Bothwell giving a lecture about some astronomy topics. He's also doing this every Tuesday. It's really good, so I think it's in the afternoon European time, so check this out on our YouTube channel. And
I think it's 2 p.m. British time, I think.
Okay. Then otherwise, see you next week again on Monday, and have a nice evening. Thank you, Sam.